Assalamu alaikum students. Welcome to the lecture number 11 for week 6 of advanced nanomagnetism course, and in this lecture we will proceed the previous lecture. So this is actually the second part of that previous lecture in which previously we have learned about the log normal distribution for the diameter and the volume, and also we have calculated the average magnetization for the blocked particles and superparamagnetic particles at temperature. So this is the second part in which we will finalize or calculate the low field magnetic susceptibility for these magnetic nanoparticles. So for nanoparticles containing 500 to 10,000 roughly oriented spins, composed together to form a nanoparticle. Just for simplicity, we can its relaxation of these nanoparticles according to Needle relaxation, and in which the particle is not moving physically, only the magnetization of the core is moving. The tau m and is the measurement time, tau naught is the atomic spin flip time, ranges from 10 to the power -9 to -12 seconds. TB is the blocking temperature, K is the effective anisotropy constant. So it's a competition between the KV and KB TB. From the above equation, for taking measurement time in squid, actually it's about 100 seconds at the threshold. Equation 1 can be from equation 1 we can find the volume of the particle, which is a function of TB, and this is written in equation 2, which is taken just by simple solution from the equation 1, taking log on both sides and then simplify for volume. So the log normal distribution, we have taken f as a function of v for the particle of volume v, can be transformed to similar log normal distribution for the average blocking temperature f of TB, as I told you, because from equation 2 you can see that they are both related with each other. So the standard deviation in the volume will be equal to the standard deviation in the blocking temperature. For the blocking temperature TB of the nanoparticles, we can write the log normal distribution as demonstrated in equation number 3, where average of TB is included. TB is replaced with V, and sigma V is replaced by sigma TB. The average blocking temperature we have taken because you already know, due to the particle size distribution in the sample. So we can rewrite the equation number 2 in the form of in the average blocking temperature, which is directly proportional to the average volume. Here we consider the anisotropy also. So K is the anisotropy of the nanoparticles. So we can have two types of low field susceptibility. One is the zero field cooled BC susceptibility. It is similar to the, we can call it zero field cooled curve, and we take it we understand it in the previous lecture. The sample of randomly oriented nanoparticles is cooled down in zero field to lowest possible temperature, and at that temperature you fix the temperature and apply a small DC field, and then the temperature is slowly increased and the magnetization is measured as a function of temperature, and this curve will be zero field cooled curve, and the field is fixed for all during the this MT curve. So for a certain selected volume of particles, there can be two regions separated, as I understand from the previous lecture. The below, if the temperature is above TB, if you are looking the above TB, the particle will be superparamagnetic state, and if the temperature is less than TB, the particles will be in the block state. So the zero field susceptibility curve can be composed into into two contributions, as I told you, for the super paramagnetic and the blocked particles, as written in equation number 5. So first one term is belong to the super paramagnetic particle, and the other term is also is for the block particle at the same time. So for the field cooled DC susceptibility curve, and the sample of randomly oriented magnetic nanoparticles is cooled down in the same field as we have taken for the field cool, and the magnetization is measured as a function of cooling temperature to get the field cool curve, because we are measuring now we are cooling the sample in the field cool conditions. That is why it's called field cool curve. Is a similar curve. The field cool DC susceptibility is written in equation number 6, where we have used the f of TB, which is necessary, and we integrate it. So we have two contribution at one time, and one is at one temperature from super paramagnetic particles, and also from the block particles. So here's the simulation, numerical simulation of field cool, zero field cool curves of previous equation 5 and 6, in which we have plotted two curves with different anisotropy constant. You can see the small change in anisotropy constant, such as k is equal to 2 into 10 to the power 6 erg per cc, and k is equal to 5 into 10 to the power 6 erg per cc. The shape of the curve is changed, and also the blocking temperature is shifted to higher temperature. This is because TB is directly proportional to K. If we increase the K value, effective anisotropy constant, the TB shift to high values. So that is needed for the small particles, and for this simulation we have only changed one parameter K, and the particle size is fixed to 5.1 nanometer. Means if we need some magnetic nanoparticles to use in the data storage, this TB, which is in this for the blue curve, is around 125, 130 Kelvin. It should be around 300 or more than 300 Kelvin above room temperature. So we want some nanoparticles, composite alloys, or some kind of particles which have anisotropy, very high anisotropy. So here is the simulation of the zero field cool curve of the same equations with the same. Now in this, now we have fixed the K value, and we have changed the diameter of the nanoparticles. So you can see, just changing the small change in the average diameter of the nanoparticles, we have a change in the blocking temperature, which means the TB is increasing with increase in the diameter of the particles, which is correct, because from this Neil-Harness equation we have seen that the TB is changing with the volume of the particle. So these two simulations are very straightforward to do in the MATLAB. You can also do in MATLAB, and you can understand how these things works very simple, and without doing any experimental work, you can calculate the effective anisotropy constant and the blocking temperature for some average particle size samples. So here's the example of some simulation and the experiment for the megamite nanoparticles of 4 nanometer. And this up triangles, blue triangles are for the experiment, and the black and the red curve is the simulation curve. You can see the simulation works very well for the zero field cool curve, how there is deviation below TB for the field cool curve, experimental field cool curve, and the experimental and the simulated field cool curve. And the effective anisotropy constant was fitted from this curve, which comes out in 16 to 10 to the power 5 arc per cc, which is higher than the bulk value, and this is normally observed in nanoparticles and well published in literature, and this is due to the fact the effective anisotropy constant in nanoparticles, ferromagnetic nanoparticles, is usually high due to contribution of the surface anisotropy. So effective anisotropy constant is normally usually equal to K bulk plus K surface. So we can find out the surface anisotropy. The effective anisotropy constant is higher than the bulk value because of the increased surface anisotropy. And this deviation in the field cool curves of experiment and zero field cool, as I told you, the model, the Storm-Wolfram model assumed only non-interacting particle in which the field cool curve continuously increasing below TB and shows a plateau at very low temperatures, while in practice we have surface defects and also interparticle reaction, and the field cool curves becomes flattened very quickly below TB. So the flatness of the field cool curve here is due to spin glass. We will learn about it in the coming lectures. So thank you students, Allah Hafiz.